Okay, this is the second part of session 16 of mathematical methods for signal processing. And I would like to give you a short description of the general Poisson formula. General meaning in the setting of RD and lattices in RD. Recall that a lattice is a discrete subgroup of the additive group of RD. So you have vectors and you can add these vectors. And one can easily show that they are of the form, take the standard integer lattice of integer pairs and apply some non-singular matrix, some d by d matrix, and you get the general lattice. For each lattice, you can look at all the pure frequencies. So it should be characters, I should have a head here, which are identically one on the lattice or at the lattice points. So these are the ones which you cannot distinguish from the so-called trivial character, which is simply just constant 1. And it turns out, if you think of the e to the 2 pi I, if you're saying, what are the points where all these exponential functions with integer frequencies, they're all together 1, then you find out it's exactly, again, the integers. If you pair a non-integer with an integer, you find at least at some places some value which is different from 1. So the orthogonal group with the 2 pi and the exponent for the integers is the integers. You do the same for sets D, you find the same thing. And if you take it more general lattice, you can compute this, that it's more or less you have to invert the matrix or transpose inverse of the matrix to get the new lattice. I would like to show you rather an image here. In 1D case, this is a periodic case. This may be a lattice, and you see it's kind of having a generating system. You take two vectors, you take all the multiples of one vector, you take all the multiples of the other vectors, and then generate a grid. Of course, also taking negative components. And that lattice has an orthogonal lattice, so to say, lambda perp, which is this one. And then you can play around, you can rotate this one, and this will be rotated. If you make it more dense, then this will be more sparse. If you make it more sparse, that will be more dense, and so on. Whereas in the one-dimensional case, we have seen that the FFT, more or less, of a Dirac comb is another Dirac comb. And probably here I would say it looks like you have amplitude 25 or so. Maybe it was a lattice with 500 points. Then you have maybe lattice constant 20. That means you have 25 points adding up, all one. So you have 25 constant. But if you take the number of these peaks, or the Fourier transform, the number of elements of the orthogonal lattice multiplied with the number of elements here, then you have exactly the signal length and here. And similar things apply here. So if we just say, well, you do the same thing now for multidimensional things, then you find the following. If you change the lattice from volume 1 to other volumes, that you can say, if you have a function in S0 of RD now, then you can sum up the values. This is convergent as well. The Fourier transform is also well defined, and you have another lattice, and that sum is also finite. But if you do this for all these functions up to some constant, which I think has to do with the determinant of the matrix A, or the volume of the lattice of the fundamental domain of the lattice, but that's not so important now, then you have up to some constant exactly the same formula, or, and that's interesting to see, if you take the Dirac comb, which normally for ordinary integration doesn't have a Fourier transform, but now has a Fourier transform, it is a member of the dual of S0. Actually, it's a dual of the Wien algebra. And this guy is as well. And then the Fourier transform of this guy happens to be this one. So I think this is an important thing that we can use. But most of the time, I will restrict my attention to either the standard lattice set in RD, or maybe you think you make the lattice finer or more coarse by changing the value alpha. And then, of course, it turns out that you have to take not 1 over alpha ZD, but 1 over alpha bracket times ZD. So it's the lattice with maybe lattice constant 3, then the perpendicular orthogonal lattice, as it is called, will have constant 1 over 3 here. So you see the density is reciprocal of these lattices. Of course, the more points your lattice has, the more conditions are valid for the orthogonal lattice, and therefore it has to be more thin, and vice versa. So this is a very, very useful thing. And when you do the MATLAB experiment, it's also interesting to see what happens, and I think you should keep this in mind. Whenever you take such a lattice, this is an example from the one-dimensional case, and you look at the Fourier transform of the pure frequencies, then, well, we have seen each pure frequency of a Dirac comb. Each Dirac comb is a sum of deltas, Dirac deltas. On the Fourier transform, this is a pure frequency. And of course, pure frequencies take values on the unit circle, actually for signals of length n, they're unit roots of order n with some exponent. There are a lot of different exponents or so. But what is the possibility? Well, if you're at a coordinate where all of the values that these frequencies that appear are taking, if they're all 1, then you're at a position in the orthogonal lattice, and you're just counting how many Diracs do I have, so many ones are adding up, and you get the same value at each of those points. But, and that's the interesting part maybe, if you're at any other point which is not in the orthogonal, then there are at least some other values, not just constant 1. So the easiest case would be there are some plus 1s and some minus 1, unit roots of order 2. But you will find out easily that they are coming in equal quantity. Maybe you have 20 plus 1, 20 minus 1. Or in such a situation, you might have, I don't know, 8 plus 1, 8 minus 1, 8 plus a, 8 minus a. So the total number of occurrences is just coming from the number of points that you have on your grid. And maybe in the extreme case, you find out that each Dirac has a different value at such a position, but still the center of gravity of these, or if you take it more formal, the geometric series of all these things, I mean, it's 1 plus omega squared or so, and you use the formula for the arithmetic, for a geometric series, it turns out to be 0. But I think it's more interesting visually to say, well, these things add up to 1. Each pair of opposite points is adding up. And even if it would be an odd term, you would say the center of gravity of a unit roots of order 7 or 13 or so, it's of course 0. That's, everything is symmetric. So you're going from coordinate to coordinate. Whenever you're at a point of the orthogonal lattice, you will have all 1s. And wherever you are else, you have things which cancel out each other and will give a 0. And so that's the nice property why you can understand why in a discrete setting, the Poisson formula is not a magic thing, but a very reasonable situation. Now, for the rest, today I would like to talk a lot about the generalized or extended Fourier transform. I jump back in the script to page 124 and recall to you that this is a very simple trick to define the Fourier transform for elements in S0 prime. And we have already mentioned that it's consistent with the ordinary definition. So if you're giving me an ordinary L1 function, turn it into a measure, and I take the Fourier transform, you get the same thing as taking the Fourier transform in the integral sense of this. You get a continuous function, but you view it as a measure. So this is just first going from ordinary objects to distributions, then taking a Fourier transform here in the sense of distribution, or first doing a Fourier transform in the ordinary integral sense and then viewing it as distribution. That's all fine. You're not getting any confusion or so. Now, the statement that I wanted to show to you is that this mapping is weak star continuous, and I think that's coming up later on. Oh, sorry, yeah. You can read yourself this part. The proof of the Poisson formula is going quite analog. You periodize with respect to the lambda, and then more or less all the arguments that we had for the one-dimensional case apply. And okay, I also told you this. The periodization in the one-dimensional case, of course, means that you're creating from, let's say, the red curve copies, which are the brown curve, violet and blue, and then the black curve is the sum. So this is a periodic function, as you see. This is periodic, whereas the red is not periodic. And that this guy you're considering as a function of a signal of length, which is a quarter of the original length. You do a Fourier expansion, that would be the basic idea of the periodization. Or you take an image, and the lattice would, of course, consist of 9 points that you would kind of see here, because you have 3 copies in that direction, you have 3 copies in that direction. But you can take other lattices which are more dense, you would lose more information. And so that's kind of what I wanted to show you. But I have to go through to the place where I tried to show the weak star convergence. Yeah, I think this is what I wanted to show to you. That the extended, this is now page 140 of today's version of the script, the extended Fourier transform is a mapping which preserves weak star convergence. Now, weak star convergence is a concept that we have seen already for bounded measures, and whenever you have a dual space, you can work with the norm. Every dual space has a norm, which is for example, the norm of a functional. But you can have a problem with this because it might be too strict, and that's where you're saying I have to apply these functionals to the elements of the underlying space of test functions, for example. And then weak star convergence means each time you insert such a test functions, you observe convergence. So I think I'm not sure. Yeah, I can explain this by recalling this proof. So what does it mean? Sigma 0 is the weak star limit of sigma n. You're giving me a sequence of this sigma n, maybe Dirac sequence or Dirac combs or so, and then you're saying, well, I want to see whether these abstract objects are convergent to this limiting object by trying to insert any f from a 0, if we are talking about weak star convergence inside of 0 prime. You apply to any f, and if this has a limit, and this is exactly the S0 of f. And so the claim something is preserving weak star convergence is if you have on the input side of the Fourier transform, you have this property, you would have to have it on the output side. Now, it's only the terminology is confusing. So I'm saying that this implication is valid, and you're challenging me, and you'll say, well, now I'm giving you such as sigma n. How can you show that these Fourier transform f sigma n are behaving well? So we look together at f sigma n. What we have to do is we have to show that if we apply it to any f, at the end of the story, we're ending up with the expected limit, which is the Fourier transform of f sigma 0, of course, applied to f. So you have to read it always if extended Fourier transform applied to a functional is something which is a functional. So if you apply it to arbitrary f, it has the same effect, then they will be equal. Now we have to see what does it mean, the Fourier transform of an extended, the extended Fourier transform of sigma n applied to f. Oh yes, definition means sigma n applied to the Fourier transform of f. But now I'm saying, well, you're telling me that you know that sigma n is weak star convergence to sigma n. So I can put any element from the Siegel algebra and you must admit that it will be convergent. So because the Fourier transform leaves as 0 invariant, if you give me any f, I can take the Fourier transform of that f, and that will be convergent by assumption. So this assumption, just saying for every element, so also for the Fourier transform of f, will go to S0 of this. And then you reinterpret the target in this. So it's essentially the trick of this jointness operation. They're always weak star continuous, and also norm to norm continuous, but that's the more interesting condition in this way. So this is a reason why we will be interested in weak star convergence, and we had already such a weak star convergence in the case of measures. Measures are another dual space, and it was this idea that discretized measures. So I'm always saying the histograms, the information in the histogram is convergent to the measure in this weak star sense, not in the norm sense, because the limit of discrete measures could only be a discrete measure, but this is true for any measure. And what was the trick? Well, we were inducing this discretization procedure in a particular way, but actually as an adjoint operator, we're saying, well, we say that's mu applied to another operator, which was a spline approximation operator or quasi-interpolation operator. But because we knew that these things are convergent to f, we could so say that the deep C mu of f is going to the action of mu to f. So this is a typical situation where you are using this. Now, I don't know whether I will go through this, but yeah, maybe I should give a short explanation. If you have now measures, and there's a difference between saying I have a bounded measure or I have a collection of measures which are bounded within the norm, which means first there's one constant for each, but here we are saying there's one uniform constant. Whenever you apply mu alpha to some function f in C0, you can control it. So that's the boundedness. And if it's the statement is if it's weak star convergent now in the new sense, in this larger space, where it means you're applying it only to a zero functions, not to all of C0, then it's still weak star convergent in the usual sense. So the trick is weak star convergence looks like it was very strongly dependent on the reservoir of functions that you use, but if you're having a dense subspace, you can test it as long as the boundedness is important, if you have a priori boundedness. So sometimes we will see that we can transfer weak star convergence to the Fourier transform side using the zero prime theory, but if we happen to get measures, everything would be fine also in this more general setting. Now, I'm making a statement or use the opportunity to prove something more general, that if you have not just a dense subspace like S0 inside of C0, but something where the linear combinations are dense in that space, that would be already enough to imply this condition. So assume you have a set of atoms, so to say, and if you take linear combinations of the atoms, you can somehow show this kind of convergence, so that the f is a linear combination of these generating elements, then everything is fine. How would you extend it to the general situation? And the answer is use the standard trick. If I claim now for an arbitrary f, and you don't have to care too much about details, I just explain the main arguments here. If you want to apply to an arbitrary f in your C0 space in this example, and you would like to show that this is weak star convergent, you have to estimate after taking the action to any f. So you give me some f, and I have to do some good job. Now, my argument is, of course, I know there's a nearby element where everything is fine, and I would like to use this. So I'm saying, well, instead of mu alpha f, which I don't know yet, I go to mu alpha k. So the difference hopefully is small. Once I'm at the k, I move the index from alpha to 0. And when I'm at mu 0, I would like to move back from the k to the f. So it's very often this triple. Now, we have assumed this family is mu alpha is bounded. So what does it mean? Whenever you insert a function with compact support, or any of these elements, not compact support, any from this dense subspace, that you can take the limit. Now, we didn't make an assumption, a proper assumption at the moment about the element mu0, because here we have to need an estimated mu0. But the point is, if all these alpha have a constant, then the same constant can be used for mu0. So what is the argument? In order to define the size of the functional mu0, we take the sup over all the elements in C0 with norm less than 1. Oh, it's not necessary to take all of them. It's enough to take them from a dense subspace. Therefore, I am allowing myself to replace the f in C0 by k from the ones where I know everything. But where I know it, the mu0 is the limit of mu alpha k. And taking absolute values is also compatible with the limits as a continuous procedure. Now each alpha, for all the values alpha, there's a common constant c times the size of k. And so if they are taken to be less than 1, this is the constant c. So the point is, I can take the same constant to pull out here and here for the first and last term. So we have mu alpha k minus f. Well, how big is the value of a functional? It's the size of the functional times the size of the input. So this is at most c times epsilon. And of course, I will make this term k minus f, the approximation, such that this term is good enough. So I choose it to be epsilon over 3c. Actually, I think I should take probably like, I make the approximation, that's probably, say here I take it. Knowing what I will need once I write the proof, at some point I realize it would be great to choose it such that the approximation is of the form epsilon over 3c. Then I can estimate this first term here by c times epsilon over 3c, which is of course epsilon over 3. Because we can control mu0, the third term is in the same way, but now we have replaced f by some k, and now we choose an index k, or alpha 0, sorry, quality measure, so compression factor, discretization quality or so, such that for every a which is better than this, we have approximation for the k with a quality epsilon of 3. So we have this term that we want to approximate or estimate is at most 3 times epsilon over 3, which is epsilon, and this is good for all these good parameters, and that's why we have this convergence. So maybe this was a bit cumbersome, but it can be quite useful. Now, I would like to jump a little bit now to the Fourier transforms. It's too fast. Yeah, what I want to show you is that the extended Fourier transform, that the kind of the main goal of the rest of today's session is, the extended Fourier transform is an extension, but it's the only reasonable extension. And in order to do this, and having already established that it's weak star continuous, I would like to show to you how you can prove that S0, this space of nice decent function, is weak star dense in the dual space. So that will be the target of this part of the section. So let us recall that S0 is a nice space which allows to do convolution with L1 and multiplication with elements from the Fourier algebra. And as a preview, because we don't have yet all the tools, I would like to mention to you that if you convolve an element from S0 with an element S0, so if you convolve a functional with an ordinary function, we know how to do that in principle, then you get a nice, decent function which has the property that if you multiply it with S0, it stays in S0. So essentially you would say those convolution products are decent enough to be pointwise multipliers in this here. Or you're saying, well, S0 prime is an element of certain objects. We call mild distributions because they're not too nasty, but they may not be decaying at infinity or so. So what you would do is you would damp them. So you multiply them to force decay. But once you're forcing decay, you're saying, well, they're not yet decent functions, but if you convolve them, you smooth them a little bit with convolving it with a triangular function, with a narrow triangular function, you're already getting a function which is very nice and everything like this. And by choosing appropriate approximate identities here, you would be able to prove the weak star density in a more elegant way. Now, the problem that I have to confess in the sense of mentioning it at least is that normally we would say, once you have all the Lebesgue integration theory available, that the dual space of FL1, L1 is just the amalgam space FL infinity, L infinity. FL infinity are the so-called pseudo measures. So locally, these are things which have a kind of bounded Fourier coefficients, and then you would have a uniform condition on this. So it's slightly more general than the dual of Venus algebra, but L infinity, the dual space of L1, has not been discussed so far. We don't want to start discussing measurable functions only for this purpose. Therefore, I'm giving now a new proof, new in the sense that that probably is not in the literature in this exact form, but it will be more close to the approach that we have already used. So what is the first step? The first step is, so I'm kind of doing something like this, but with one extra convolution. First, I'm saying, well, let's look at the convolution between functionals and test functions. And what you expect is, of course, that you can control it, that you're getting continuous functions. And it's, again, we will see, we'll get uniformly continuous bounded functions. And there's a natural norm, the size of the functional times the size of the function. Now, the first thing is that we will say, well, how do we do the convolution? I mean, we can say we introduce a new convolution, more or less what we will do later in a moment. Or we can say, no, we know already that S0 is inside of L1. So S0 convolved with S0 prime, and as you know, by now we can change the order without any problems, should be understood in the sense of L1 with S0 prime, or bounded measures actually applied to 0, 1. How would you do it? Well, we would do it by the adjointness relationship. We would say, well, we know that bounded measures act on S0, and then we are doing the adjoint action. And as we have learned before, and that's one of the reasons why we're doing that in great detail before, you can define mu convolved with sigma. Strictly speaking, this is a new extended version of convolution, but we have seen it's always compatible with with any other one, is the same as sigma of mu flipped with this. So it's like the adjoint operator is given by the transpose matrix, more or less like this. So, well, we know this is a bounded operation on S0. Taking a functional is bounded, therefore this new functional, which we name mu convolved with sigma, is okay. Now, of course, you also have to check, is it true that mu1 convolved with mu2, internal multiplication, and then convolved with sigma is the same as first applying mu2 with sigma and then mu1, so it's 2 external multiplication. But also this has been done, and how would you prove it? It's okay when you just do translation using convolution with Dirac measures, therefore with discrete measures, therefore taking limits. So we don't have to go through the process again. Now, the point is that we also have a machinery and checked in carefully that if you take a measure and apply it, coming from a nice and decent function, you could also do the pointwise convolution. And how would the pointwise convolution do? If you convolve a functional with an element from the underlying space, You just say, I can apply the functional to the test function, first flip, then shift it. And so this is what you have to verify. Is there's an abstract definition of convolution, but if we do it pointwise, you get another thing. I mean, the point is, I'm claiming this is a bounded and uniformly continuous function. I call it H, this pointwise product. And of course, the abstract convolution is giving you a measure, a functional, which is, of course, the functional introduced by this function. If you want to have the action of this on a function f, you would just integrate your function h against f. And so this is kind of all we have to do. So if we concentrate on this, it's quite clear that a pointwise product, and that's exactly like this C0 bounded measure proof. Pointwise product is, well, you're applying the functional sigma to a flipped and shifted version of k. But flipping and shifting is isometric on this zero, or at least uniformly bounded, therefore you can control it. So maybe of a constant here if you take a different norm. But if this is true for every y, it will be true for the supernorm. So we have boundedness. How can we prove continuity? And well, the answer was already for C0. Let's prove uniform continuity. And the argument is exactly the same. The shifted version of this pointwise product can be compared with the original pointwise product by observing that also the pointwise convolution is commuting with translation. So you can say, oh, instead of shifting the convolution product, I shift only the k. So you can pull out the TCK and convolve it afterwards with sigma or the k. What is the difference? Distributive law is the size of sigma, that's some number, times T set k minus k. Now, this is the place where it's good to know already that in the zero norm, the shift is continuous. So this will go to, it's only for elements from S0, but it is also in this strong and sensitive S0 norm. So it's not obvious, but it's clearly true. And you can say, if you go back to the argument, the compactly supported elements in S0, for them, more or less, the S0 norm is the Fourier algebra norm. So doing it in the Fourier algebra norm is fine. But we have already, in the summary of all the properties of S0, we have this property. Okay, so this is going to zero, meaning the difference is going to zero, and that was the early characterization of uniform boundedness. Now, what I'm doing here is I'm not just convolving, but then I'm also localizing it. But by doing this and avoiding the more complicated theory, I'm getting not enough to be inside S0, therefore I'm doing one more convolution. So I'm using a shortened notation. You can think of G rho being the compressed version of the G0 and G upper rho the dilated version. So exactly the two guys that we were using for the proof of the inversion theorem are invoked now. And I'm saying, well, if you give me your sigma, and I would like to approximate it in the weak star sense, meaning after application it to finitely many f's, I would like to be able to show that the difference between this more complicated object, which is interpreted as some element of S0, and the original sigma is negligible. It's smaller than epsilon for those finitely many test functions, given test functions. Okay, now what you're doing here is, the philosophy is, well, I convolve my sigma with a very, very narrow Dirac-like function. Well, if this is an approximate identity, so I can hope that this is more or less like sigma convolved with delta at zero. So it's like sigma, a little bit smeared. But then you're saying, but also maybe this is not good, and I multiply it to obtain finite support, for example. So I'm taking a hugely stretched triangular function, which leaves a lot of area intact, but it produces compact support. So this guy, as we have just derived, is a continuous function with compact support. This is can be chosen to be a compactly supported guy. So if you take delta, for example, the delta function. So this is altogether a continuous function with compact support, which may not yet be in S0. I mean, we don't have an argument. I know personally that it's okay, but the explanation is more complicated than just to add one more smoothing, which pulls ourselves from L1 into the S0 space. So what I'm using here is the first convolution product in square brackets is in UB, in CUB. Then you take the pointwise multiplication with an S0 object, and that's like multiplying S0 with UB and then convolving. Now S0 is inside the Wien algebra. So that's maybe I should have written here. So if you take something in the Wien algebra, absolute, I mean, nice upper Riemann and sum, and multiply it with a bounded function, you're staying in the Wien algebra. And then you're taking the second S0, which you convolve. But that's like convolving with an L1 function. So L1 with Wiener is inside, okay, you can take both roles. I was using this argument. Wiener is inside L1, and therefore we're inside S0, and therefore it's in S0. Yeah, okay. So kind of this was this star is the second one. So if you look in a quiet moment what I'm doing here, you will recognize that this right term is okay. But why is it small? And I mean, I was saying I wouldn't write out all the details, but at the end I was really doing a lot of these things. So we are manipulating our sigma, convolving and multiplying it. And I just was recalling, how do we do this? How can we do an arbitrary distribution, mild distribution, be convolved? Well, we put it to the other side. Now, I would suggest to choose the G, I would think of the triangular function as a symmetric function. So normally you would have a flip here, but we can ignore it because it's a flip invariant. There's the same thing if you dilate it here, you can apply to dilate it here. So if we, yeah, maybe I'll leave this out. If you're giving me now finitely many functions f1 and fn, f1, f2 until fl, you would like to see convergence. So I would say, well, we're having 7 people. Everyone is taking one f, and I try to give an argument which is valid for all these people. Now, by moving from the action on sigma over to the f, we really have to look at what happens at these values. I'm not doing the triple machinery, but the double one. So if you just do first a convolution on sigma and then a pointwise multiplication, of course, if you move it over, it's opposite order. You're saying first take the f, multiply it with a huge triangular function and convolve it with a very nice narrow Dirac function. And then, of course, this is a fixed sigma element to something like this. So maybe we can apply it to this here. And now you have an iterated thing of 2 approximate units, one pointwise, one by, and we only need that they are uniformly bounded. So it's the trick for something like, which I have an abstract argument again, but let's do it directly. We have this double thing, and by not changing both of them, we change maybe from f to 0f, and then from 0f, that's 0 with f, to 0 convolved with the multiplied G upper row multiplied with f. So it's just inserting an extra term and triangular inequality. The extra term was 0f. That's coming here, minus here, plus here. Okay, now what you can get here is clearly that you're saying, oh, okay, I am convolving with G row. But convolving with G row, you just pull out the L1 norm. But the G row is a compressed element of the original and approximate unit. So it has L1 norm 1, if you choose it reasonable, and you compress it. All these guys have L1 norm 1. That means this term can be expressed independent of the row, and that's very important. Independent of the row by this norm. Bracket is nonsense. So by pulling out the L1 norm, which I didn't write anymore, you can say this, and this of course is also made small. Now you stretch large enough, so rho is less than 1/100. You compress strong enough, rho is less than 1/200. Take the minimum of the two expressions, then both inequalities will be valid. Of course, you make the first and the second term for all those finitely many elements, f1 to f last, smaller than epsilon, and the sum will be 2 epsilon. So in this way, you can show that this new element, so now the second step would be one more convolution, but that's by the same trick. This guy, which is a distribution coming from a function in S0, will give you almost the same effect on the fk, on this test function, up to some epsilon as you want. And that's exactly the weak star convergence. So we can use this now combined with another trick that we know already to show also that the finite discrete measures are weak star dense. So they're very, very thin. I mean, you need only to know what Diracs are doing, and then you have the finite discrete measures. And of course, the trick is quite adding up. First, you approximate your sigma that you're given, which should be close to some discrete measure whenever tested to those finitely many f's. And because we know already that the S0 space is dense, then we say, well, we can first approximate sigma by some nice functional coming from a nice function. But if it's a nice function, it can be approximated without loss of generality by a continuous function with compact support in S0 if you want or not. But that means you can just now apply the discretization operator. Well, it gives you one more epsilon, but if epsilon is arbitrarily small, it's not 2, but 3 or 4 epsilon. So that's no problem. So what you are simply doing is apply the discretization operator. Now, of course, the abstract parameter is the level or the diameter of the partition of unity of the poopoo that you do. But we also know that, let's say you take a triangular function very much compressed, but applied to a continuous function with compact support, you get only finitely many discrete measures. So that's kind of just a combination of what you have by the first step. And actually you could use kind of the first half of the proof only without the properties of S0 to approximate the measures, the mild distribution by compactly supported continuous function, and then you discretize. Okay, so we have this property. I don't go through the details and leave it to you. And I would like to mention, because this is also quite plausible, that you can extend it even to the finite, now to the discrete and periodic measures. So whereas you can think of finite discrete measures, well, there's a finite family of discrete points and you do a weighted sum of Dirac measures. So on the one hand, because we are approximating arbitrary objects, you may have 7 million of them, or 500 in a numerical scheme or so, but essentially they're finitely many. They're living in some domain or so. And the question is, well, what does it mean periodic measure? Well, you're repeating it, but with a fairly large period. So let's talk about the little story. Assume all these, I don't know, 700 points are living in the interval from -100 to +100. What if we shift them by 1,000 to the left, or I mean multiples of 1,000, make it periodic with period 1,000? I mean, the test functions which are in S0 will not take notice of them. While functions in S0, like a Gauss function, do not have to have compact support, but, and that's again this standard approximation argument, if we can test on compactly supported functions, then we can extend this claim of convergence also for arbitrary, this weak star density to arbitrary ones. So the trick how to go from finite discrete measures to discrete periodic measures is to say, well, we only test it against functions f1 to fl, which have compact support. So yes, maybe the biggest guy of them has support in -500, +500, but still, it doesn't see the copy that we put at 1000 plus 1 and -100 or so, or even put further out. So we can replace the discrete measure by a periodic version with a huge period, and we are talking about periods going to infinity. Now, in this statement, I'm not saying that the space of periodic discrete measures is weak star dense, because it isn't a space. If you give me even a Dirac comb sitting on the integers, and you're adding it with a Dirac comb sitting on the lattice, which is irrational, like square root of 2 times integers, the sum is kind of almost periodic in a verbal and even in a mathematical sense, but it's not having any common period. Therefore, you have to talk about the set of all discrete periodic measures. If somebody is giving you a finite set of test functions, the finite epsilon, we are able to come up with a statement that all sufficiently good local discrete reproductions of sigma periodized in a sufficiently coarse way will be not viewed as okay in the sense of being a good reproduction, but it's not an approximation from a dense subspace. So you see what I'm doing here is I do my localized discrete measure. So to be safe, I was saying I take the continuous function with compact support, which was approximating already, but viewed as a measure, I discretize it and I make it periodic so that I get a periodic discrete measure. My point will be that, here is the remark about square root of 2, it will be that the Fourier transform for periodic and discrete measures is something that pops up in the context of the discrete Fourier transform or the fast Fourier transform. But as we will show, it's also part of our discussion. It's part of the 0 prime Fourier, extended Fourier transform. And by knowing, and that's the reason for this statement here, by knowing that this collection is weak star dense, we know that if you just say, I have knowledge about the Fourier transform on those discrete finite measures, then I have no other choice of defining an extended Fourier transform in the weak star continuous way, so preserving weak star. So essentially, we have most of the building blocks now that would allow us to say, if we start from ordinary Fourier series theory, make the period going to infinity, or we start from linear algebra, FFT, or we are starting from where we started, composition of translation invariant systems, all these convolutions and their diagonalization to go to the Fourier transform domain, they are always have to be compatible, and then we'll come to the extended Fourier transform, which, on the other hand, if you already heard about the Laurent-Schwarz theory, is a restriction of the theory of Laurent-Schwarz, but we were not using the fancy tools that he was doing. We can do more or less all these things also in a more general setting. And I think that's a good point to finish now. And so the promise for next week is to relate the discrete Fourier transform back to this extended Fourier transform, and to tell you that if you give me a discrete periodic signal, which is a sequence of Dirac combs typically sitting on the integer lattice with amplitudes which are, coefficients which are periodically repeating themselves, then these guys have a Fourier transform, and you can compute it exactly using the FFT routine. And that's one way also to compute continuous Fourier transform by applying it to samples. But all this has to be discussed next time, and therefore I'm concluding the recording now. Thank you for your attention.